All right, we start a new unit today. Unit 7 is dealing with differential equations. And we start off with this first question, what is a differential equation? All right, differential equations are equations that involve x, y, and the derivatives of y. So here would be an example of one. dy dx equals x squared y squared. That's a possible example of a differential equation. Notice one of the giveaways to a differential equation is this right here. When you see that dy dx, you're thinking this could be some type of differential equation. All right? I could also have, as another example, dy dx equals 6x squared plus x minus 5. That's another differential equation. All right? This thing, all right, and when we've been doing our integration, all right, we've had a function dx. This thing can also be called a differential, all right? And so what we're going to learn is that we can think of this dy dx, we can actually think of it as a fraction. And we will learn how to do that in this unit. So let's review real quick variation. All right, let's recall. Direct variation, we did this in pre-calculus. Direct variation, y varies directly as x, or y is directly proportional to x, always turns into this. Y equals kx, or f of x equals kx. And we call k the constant. K is the constant of variation or the constant of proportionality. We did that in pre-calculus. And if it's inverse variation, the only thing that changes is instead of kx, we have k divided by x, if we're told that it is inversely proportional. All right? So the reason I'm going over that is because of some of these modeling questions that we will have today. This looks like a big, long, worrisome problem, but it's really not. Catherine runs around a linear path. Her position is given by the function p of t, where t is measured in seconds since she started running, and p is measured in miles. During the first second of her run, Catherine's acceleration, all right, is proportional to the cube root of the time since she started running. Write a differential equation that describes this relationship where k is a positive constant of proportionality. All right? So her acceleration is proportional to the cube root of the time. And already we're most of the way done with this problem. Now, all I need you to remember is that isn't acceleration, is it the first derivative or the second derivative? It's the second derivative. So what I need to put here is the second derivative of p, which, if you remember, we write it like this. All right? And so, other than that, that problem is done. There's our equation. Okay? Let's look at another one. Bacteria in a certain culture increase at a rate proportional to the number present. If the number of bacteria doubles in 3 hours, in how many hours will the number of bacteria triple? Write a differential equation that describes this relationship where k is a positive constant of proportionality. Well, this is just dB dt equals k times b, because of this first sentence right here. The rest of that stuff would be, we would use that if we were actually going to solve this problem. We don't need the rest of it to write this equation. All right? Let's keep going. A rumor spreads among a population of n people at a rate proportional to the product of the number of people who have heard the rumor and the number of people who haven't heard the rumor. Okay? So let's call our population n. Okay? If P denotes the number of people who have heard the rumor, which of the following differential equations could be used to model the situation with respect to time t where k is a positive constant? Okay? So it spreads at a rate proportional. So that sounds like dp dt. All right? dp dt. It is equal to the number of people who have heard the rumor, okay, and the number of people who have not. So that's just Kp times n minus p. This is P is the number of people who have. Okay, these are the people who have heard the rumor. All right, and these are the people who haven't. These are the ones who haven't. All right, so that's kind of the idea of topic 7.1. All right. And we will stop there for today.